Well, last time we talked about how sometimes our regular Cartesian coordinate system, our x and y's, or our x, y's, and z's, sometimes they're not well suited to performing calculations, okay? Because not everything is well suited to the Cartesian coordinate system. It's very blocky, north, south, east, west. That's good for some things, but for other things, it isn't. In particular, the example we looked at was this integral here, where we wanted to integrate this function 1 over x squared plus y squared over this region R, which is this annular region between these two quarter circles. Now that's kind of an awkward situation to describe in Cartesian coordinates. Having a combination of squares in the reciprocal is awkward. Trying to describe circles with Cartesian coordinates is kind of awkward. You end up having to talk about square roots of sums of squares. So it's not very well adapted for that. But we have this much better coordinate system for this kind of situation, which instead of locating a point as x's and y's, locates it instead as a radial distance from the origin, which is r, and the angle that the radius makes with positive x direction, which is theta. So these are the polar coordinates. And these are much better for talking about circular stuff or round stuff than the Cartesian coordinates. So they'll be much easier to describe this region in terms of square of the radius. So 1 over r squared is a simpler expression to deal with than 1 over x squared plus y squared. So how does this, okay, so the description looks easier in polar coordinates, but what about the integral itself? Well, we have this rule for how to change coordinates in an integral. So if we have our original integral as a function of x and y over a region and evaluating it with respect to x and y, we can translate it into the other coordinate system as follows. So here it's presented in general. The new coordinate system is indicated as s and t. So we replace x and y with their equivalences in s and t. We got some function x in terms of s and t, and y in terms of s and t. We still got the same region. Of course, we have the new pair of differentials, ds and dt, and then we've got this extra factor. This extra factor comes in to compensate for the different ways that different coordinate systems handle sizes of areas. Okay? This extra factor is the absolute value of the determinant of the Jacobian matrix of the transformation from one coordinate system to the other. Okay, so this is just still recap of last time. We worked through this example, 1.21 last time. And after we did the translation, this original integral suddenly became a lot nicer. It's suddenly just the integral of 1 over r dr d theta, which already is a win, okay? Because you can integrate that simply. 1 over r integrates to logarithm, and there's no thetas at all, so the logarithm just it just integrates to theta. So the integral is easier, and the description of the region was a hell of a lot easier. This annular region is everything between theta equals 0, theta equals pi over 2, and everything between radius a and radius b. So it actually looks like a rectangular region in quotes. It's a rectangular region in terms of this coordinate system, meaning a region bounded just by 2 plain old constants for each of the variables. Just like a regular Cartesian rectangle is determined by just 4 numbers if you've got a regular rectangle aligned with the coordinate axis. So that was our example last time. But we'd like to show you some examples in a 3-variable setting as well. That's what we're going to look at now. A 3D example. 3D example of changing coordinate systems in an integral. So we're going to consider the subset R contained in R3. I'll attempt to make a drawing of it here. And we're going to initially describe it in terms of the Cartesian coordinates. So this is kind of like this inverted bell-shaped, not inverted, just a kind of bell-shaped region of R3. It's bounded by the z equals 0 xy plane. So it just comes down onto the floor. The floor is the xy plane located at z equals 0. So it's bounded below by the xy plane at z equals 0. And the paraboloid, so a paraboloid is like this three-dimensional analog of a parabola. And this is defined as rho squared equals 9 minus z. So where rho is this rho is the projected radius of a point in 3 dimensions. Rho is this. Rho is the variable featuring in the cylindrical coordinate system. The projected radius of a point onto the xy plane. Or in other words, it's the kind of like the horizontal radius of a point away from the z-axis. Yes? Sorry? That's a 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. It's regular old 9. So that means the tip of this hat is located at z equals 3. Okay? So when z is equal to 3, no, sorry, when, z equals 9. When z is 9, rho is equal to 0. And when z is close to 9, you've got a very small radius that's near the top of the bell. The horizontal radius, the projected radius of the point is small. But when z is 0, down near the bottom, you've got a wide radius at the bottom. So where is it cutting the axes? This is at the value. What's the radius at the bottom when z is 0? It's rho squared equals 9. So the radius is 3. So that's x equals 3 there, where it cuts the x-axis on the ground floor. So that's our shape. It's defined. It's the part of this paraboloid cut off by the xy plane. And what we want to do is compute the integral So it's a triple integral. We've just been doing double integrals over regions in the plane. This is a triple integral over a region in R3, which is a three-dimensional part of R3 volume. So we're doing the triple integral over R of rho squared dx dy dz. So it's initially presented as an integral in the Cartesian coordinate system. However, we don't want to stick with that coordinate system, okay? Because the stuff looks kind of roundy. It's a roundy volume. And this is kind of roundy too. Okay, this isn't quite the radius, but it's the projected radius. It's a radius-like thing. Rho is the distance from the central z-axis core out to the point. So that's the projection of the actual radius. The actual radius of that point, let's add into the diagram. The actual radius there when you project that down onto the xy plane, you get this projected radius, which is just the projection down of that row. But this is kind of like a radius thing. So things are looking kind of circular and round. But now the coordinate systems we introduced for 3 dimensions, I introduced them a few lectures ago when we were looking at the chain rule. We introduced 2 in 3 dimensions. We have the spherical coordinates, sometimes called spherical polar coordinates, and that was based on describing things in terms of spheres. And we also have this cylindrical coordinate system, and that's the one that looks most appropriate for here. Okay. So this needs transforming into the cylindrical coordinate system. The cylindrical coordinate system was rho, theta, z. Okay, for theta, you look at the projected radius down onto the xy plane. Theta is this angle here that the projected radius makes with the positive x-axis. That's the angle theta. Rho is this horizontal, this projected radius value, and z is just that same old Cartesian z coordinate system. This is what's called a cylindrical coordinate system. And this is the most appropriate one to describe this because, well, one of the variables rho is featured there in the integrand, and it's also featured in the function describing the boundary of the region. The transformation equations from the Cartesian coordinates to the cylindrical polar coordinates are x equals rho cosine theta, y is rho sine theta. Well, z is just z. Z is the same. It's the same z coordinate featuring in the Cartesian coordinate system of the other, and the cylindrical coordinate system. So in order to do the translation of the integral, we require the Jacobian determinant. Okay? Because that's the extra factor that we have to include in the new integral. So the Jacobian determinant we need to work out is d xyz d rho theta z. So this is going to be the determinant of the 3x3 matrix of partial derivatives. So it's a determinant. It's 3x3. The old variables index the rows, and the new variables index the columns, and you've got all the various partial derivatives there. The old coordinates with respect to the new ones. So across the top row, you've got dx d rho, dx d theta, dx dz. Then you've got your y row, your y row, dy d rho, dy d theta, dy dz. Then you got your z row, dz d rho, rho, dz d theta, and dz dz. Now this won't be as bad as it looks. 3x3 determinants, are potentially nasty, but this one will turn out to not be too bad. So all of these entries here come from differentiating the appropriate transformation equation with respect to the appropriate variable. So what's dx d rho? Dx d rho is simply cosine theta. Dx d theta is minus rho sine theta. And dx dz, well, you look for the z's here, and there aren't any, okay? x is independent of z, so dx dz is 0. dy d rho, well, you just see a constant times rho. So the derivative is just sine theta. dy d theta is rho cosine theta. dy dz, again, is 0. There's no z and y. dz d rho is dz d rho? 0. Yeah, so there's no rho in z. dz d theta, 0. dz dz, 1. The derivative of z with respect to z, simply 1. Okay, so that suddenly this determinant looks a lot better than it might have been. So of course there's a one, you should expand it along the third row or third column or third row. And basically it's just saying it's equal to this. The determinant in the upper left. That's what you get when you expand it along the third row, say. And when you do it there, you get the value rho. Okay. As you get rho times cosine squared plus sine squared. Cosine squared plus sine squared is 1. All good? So we've got our Jacobian determinant. It's come out quite nicely as just the quantity rho. We look to the original integral. The function is already transformed because the function we're integrating is just rho squared. So that's already translated. We have to translate the region, all right? I'll just put the region in the picture there so we can see it. So the integral I in cylindrical coordinates is rho squared. Then the absolute value of the Jacobian is rho. And then you've got your d rho, d theta, dz. Okay, so it's a triple integral. So we've got 6 limits of integration to decide upon. You work, as I've always said, you work from the outside in. So what these limits of integration have to do is they have to capture this portion of 3-dimensional space in the paraboloid there that we want to integrate over. So you work from the outside in. The outside integral, remember these are nested integrals. So the inner integral is the rho integral. And then outside of that, containing that, you've got the theta integral. And then containing the other two, you've got the z integral. So you work from the outside in. So you first look at z. So you ask yourself, between what values of z do you have to integrate in order to capture that region? Well, there's bits of the region all the way down to z equals 0, and bits of it all the way up to z equals 9. You don't need to integrate outside that interval between 0 and 9 of z. So z, you're integrating from 0 to 9. Now the outer z integral, the inner integrals are a function of this z. So the outer integral supplies the z value to the inner integrals. So you think of now, at a given value of z, so z is the height. So at a given height, z, what are the limits for the theta variable? You have to choose the limits that will capture or take in all the necessary parts of the region. So you imagine yourself at a certain height, say this height here, where I've drawn the little rho radius. So what angles do we need to consider everything inside the bell? Well, we have we have to consider all angles, because the bell is kind of all around the z-axis chord. So we need to integrate theta from 0 all the way around to 2 pi. So theta goes from 0 to 2 pi. Lastly, the rho integral is lying inside the other two. So the rho integral is a function of, potentially a function of theta and z. Okay? The outer integral and the first inner one supply values of z and theta to the inner rho integral. So we might see theta and z featuring in the inner rho integral. So what are the values for rho? So at a particular height z and at a particular angle theta, which is already kind of helpfully there. So we're at this particular height z, we're at this particular angle theta. So we're interested in this kind of radius, not exactly the radius, this projected radius line. How much of it do we have to integrate along to capture the region? Well, we want to start at rho equals 0. We want to start coming off the z core of the bell, if you like. We want to integrate beginning at rho equals 0 all the way out until we reach the boundary of the surface. And the boundary of the surface was set up here to be when rho squared is 9 minus z. There is no theta featuring here in the limits for rho because it's symmetrical all the way around at the various angles. When you look at it from above the z-axis, it just has a circular outline, a circular cross-section. So it's the same at all angles theta. So the theta won't feature, but the what do you call it? The z will. So we need to integrate rho from 0 up until the square root of 9 minus 7. So we haven't completely avoided complications of square roots and that, because we do still have this Cartesian coordinate z. It's attempting to describe something circular, so we do still have kind of z square roots and squares and so on. But it's not too bad. Is that okay? Any questions on deciding on the limits there? You just have to take your time with it and set it up carefully. So it's a triple integral over the same region of the same function translated to the new coordinate system. Okay, it already was. You've got the absolute value of the Jacobian determinant. Okay, we don't need the absolute value signs because rho is a length. It's a radial length. So it's always going to be non-negative. So we can drop the absolute value signs. Then we got the three differentials. Then you decide on your limits by carefully looking at the region and working from the outside in to set all the limits up correctly. And then you just got to start integrating. Okay. And then to actually carry out the integrals, you generally work from the inside out. Because this is the inner integral. Now the inner integral is the integral of rho cubed d rho. So that won't trouble us too much. So that's going to be rho to the power 4 over 4. And that's evaluated at rho equals 0 and rho equals 9 minus z. Can be helpful just to name the variables here that you're making these substitutions for. Okay, it's not really needed here because I've only got one variable here, but in general, you might have a few variables floating around here. If you've just done a rho integral, these limits are for substitution into the rho variable, not any of the others. So you can emphasize that, stop yourself mis-substituting them by putting the equations for the limits there. So this is going to be, what's this going to be? Integral 0 to 9, integral 0 to 2 pi. So you make this substitution, so you get nothing at rho equals 0, and you get the square of 9 minus z at there. So it's going to be 9 minus z all squared 4 d theta dz. Now, of course, now the integral to do is the theta integral. Of course, there's no thetas there in that integrand. So working efficiently using a property of integration, that integrand can slide outside, can't it? Because it has no thetas in it. It's just a constant as far as theta is concerned. So it can just pop out here. It can't go past this integral because this is the z integral, and there is z in it. So you just got the integral from 0 to 2 pi d theta. So that's just the value 2 pi. And that 2 pi, because it doesn't depend on z, that can immediately slide out here. And let's slide the 4 out as well. Get rid of that. So it's just the integral of the square of 9 minus z. Which probably isn't too hard. I guess we need to square it out to stop going wrong. So it's 81 minus 18z plus z squared. Z. And that is whatever it is. 81z minus 9z squared z cubed over 3. Evaluated at 0 and 9. So the integrals are all done. Just have to finally substitute 9 in there. These cancel. It's been 9 by 9 by 9, then you have 9 by 9 by 9. So they cancel. So it's just 9 cubed over 3, which is 81 by 3. Just whatever it is, 243. No? Yeah, 243 over 2 pi. Okay. So that's a good example of applying this translating integrals thing to 3 dimensions. And well, we might do another example this evening. I'll be giving the lecture at 5 o'clock. I'll take any queries about the coursework you might have then as well. If you want to try and clarify anything. And I've got another nice 3-dimensional integral using spherical coordinates to show you. And we may make a move on to the next section on Green's theorem as well this evening as well. Okay, we'll leave it there for this morning. We've got a few minutes. If there's any individual questions, feel free to come up.